At a sapling question, it is an alkene, and they wanted to go to, there's an OH added, and you create an ether, and these two things are trans to each other. So the relationship to see here is that the OH and this thing added, right, those are the two things that are added, are trans to each other. So that should make you think, well, either how do I make things trans to each other from an alkene? So it should make you think of, right, so there's no bromine here. What's the other thing that you get trans stuff with? The oxygen thing? Epoxide, right? Yeah, it's had to come from an epoxide. So one of the ways to make epoxides, right, is MCPBA. It's also written as R or phenyl CO3H. If you see the oxygen, the three O's, that's per benzoic acid, that's MCPBA. So the O3, that adds an oxygen. That makes the epoxide from the alkene. And then the last part you need, now you gotta be careful here, right? Because you wanted to add to the, right, if we number these carbons 1 and 2, you notice carbon 2 is less substituted. So if you want to add something to the less substituted side of an epoxide, do you want to do that in acid or base? Base when you want the less substituted side. So you'd want to use O minus, right? If you wanted to add this part to carbon 1, you'd use H plus, and this as just the alcohol, right? So a couple layers of questions there, right? This makes an epoxide, right? To make a trans alcohol, it's an epoxide idea. And then what side of the epoxide you attack is based on whether you have base, then you go less substituted. If it was an acid, you go to the more substituted. This is probably from exam 3. There's a question like this, showing two epoxides and products, almost exactly kind of like this, actually. You should fill it in.
Wait, is it possible to do?
So let's do a practice aldol. Let's do an aldehyde plus a ketone, and let's use OH minus, so a small reactive base. Right, so we're looking for alpha hydrogens here. Right? We have aldehydes and ketones, so we're looking for acidic alpha hydrogens. So the aldehyde here, does this aldehyde have any alpha hydrogens? No, because this is not an alpha hydrogen, right? No. Absolutely not. But what about this ketone? Does it have any alpha hydrogens? Yes. How many? How many types? 2 types. So which one are we going to pick, though? So this is tough. So we have a small reactive base. So what kind of enolate are we going to make? The kinetic or the thermodynamic? Thermal. Small, we're going to go for the most stable, right? So we're going to take the H from here. Right? Small reactive base, we take from the more substitute side. So we deprotonate. I'll draw it this way this time. All right. So now we have our nucleophile. The carbon of the carbonyl is going to be our electrophile. So let's have that react. Simply an addition reaction. All right, so we make a tetrahedral intermediate here. So you have an O minus, which still has an H bonded to it. Right, probably be really helpful to number carbons here. 1, 2, 3, 4. So if this was 4, that means this had to be 3, 2, and 1. Let's make sure I haven't lost any carbons along the way here. So far looks pretty good. So you have a tetrahedral intermediate. You ask yourselves, what's the best leaving group? Is there even a leaving group here? Nope. So usually the second step in these aldols, so along the way, right, we made water. So this can take that H, And sometimes the last step, they'll treat it in H plus and maybe a little bit of heat, right? But to maybe do an elimination. But in this case, right, to do that elimination, you need to have what? You need to have alpha hydrogens, right? So if this is our leaving group, we need to have beta hydrogens that are also, so beta hydrogens to this, which are alpha hydrogens to the ketone, right, to do an E2 or do an elimination. But there are no hydrogens here, right? And there's no hydrogens here, actually, either here. There's no beta hydrogens here either. So there's no way to actually do this elimination. So that actually, in this case, this would lead to nothing. So this is the final product. Right, so if you look at this, what sorts of things to look for? Your nucleophile stays as a carbonyl, and your electrophile becomes, right, an alcohol, or it gets eliminated. But notice where the nucleophile ketone, the alcohol ends up on the beta carbon away from it. So you can start to recognize that, where there's a pi bond between alpha and beta. But the OH is always, right, on the beta carbon from this carbonyl. Taking a look at number 8 from exam 4 from this year, 2015. This is a Wittig reaction, right? So basically this is asking, do you understand how to form the Wittig and all those, how it works? So the first thing we have in here, we have phosphorus with a plus charge. We have R3, and there's a Br minus to balance our charge. In step 1, we use N-butyl lithium, which is a really strong base. In step 2, we treat it with a carbonyl. So even if you don't know the mechanism at this point, you should be able to draw the product. Right? Because if you remember what a Wittig does, right? A Wittig takes a carbonyl and turns it into an alkene. So whatever's on the phosphorus becomes part of the pi bond. Actually, this carbon right here was. So if I remember that 1 and 2. So ideally, you'd be able to look at this and say, well, I know I'm making this, if this is 1 and 2. Right? You should just be able to look at that and say, boom, that, ideally. So the mechanism, though, so how we get to this point, so to do that, this carbon, if I finish numbering these carbons, 3, 4, 5. 4 is an electrophile or nucleophile? Carbon 4. Electrophile. And it looks to me like in the product, 1 and 4 need to be bonded together, right? So if 4 is an electrophile, what does 1 have to be? A nucleophile. So I need to make carbon 1 nucleophilic. So because it's next to this plus charged phosphorus, this H here actually becomes acidic. And because this is a, right, carbon bond to lithium, remember where lithium's at the periodic table, lithium, right, is far to the left, right, really this is like a C minus. This is more like an ionic bond. So it's going to take that H, right, in an acid-base reaction. So nothing happened to the phosphorus, it's just kind of along for the ride. There's a minus charge now on carbon 1. Right? You made butane, right, which is a gas that just bubbles out of the solution, right? That's where, right, this carbon right here essentially had a negative charge and lithium had a plus charge. What else did you make? What salt did you make? Literally come crashing out of the solution when you run this reaction. Lithium bromide. Right? This is a gas, it'll bubble out. This will be a salt. And now we turn carbon 1 into a good nucleophile, which we needed to do. So the next step, let's have carbon 1 attack carbon 4. But now in the Wittig, at the same time, this pi bond comes back around and attacks the phosphorus, because oxygen likes to be bonded to phosphorus. And you form this somewhat strange looking 4-membered ring. And the charge is gone. So we number our carbons. So 1 is now bonded to 4, which is still bonded to 3 and 5, and there's 2. Right, so the charges went away because phosphorus essentially expanded its octet. Phosphorus is lower on the periodic table, so it can have 5 bonds and be happy with that. So the charge is gone, right? We've balanced our charge, right? Because overall, this was plus and minus, that's neutral. Overall, here it has to be neutral. And now we need to break it down. So phosphorus and oxygen want to stay bonded. So let's break the carbon 1 to phosphorus and carbon 4 to oxygen bond. So it gets us the product we predicted. And phosphorus with a pi bond, double bond to oxygen. And those 3 R groups still along for the ride there. That's what I was looking for there. So number 44 from the 1998 ACS. This is asking us which reaction is not an example of electrophilic aromatic substitution. So before we even look at the questions, let's define EAS, electrophilic aromatic substitution. What do we know about that before we even look at the answers? What do we know about electrophilic aromatic substitution? So what's the point of this?
You get rid of one thing and replace it with another.
And specifically, right? So it's a substitution. So right, it's a substitution. So we're doing a replacement, right? So we're replacing something, but what specifically? A what?
Aromatic.
An aromatic ring. Substitution on an aromatic ring. And what are we always substituting on the aromatic ring? So what are we trading out? What was on the ring that we're getting rid of? An H, right? Substitution on an aromatic ring of H. Good. Perfect. What's the nucleophile in electrophilic aromatic substitution always? The ring is always the nucleophile. Ring, nuke. Good. Perfect. Now let's look at the answers. So all of these appear to me, are they all replacing an H with something? Yep, that's true. The ring would have to be the nucleophile. Now wait a second. The ring has to be the nucleophile on all of these. So if we look at these on number 44, one of these kind of looks weird as far as the ring being the nucleophile, right? Because there was a set of reactions we learned about where it was really hard to say something was a nucleophile or electrophile. What were those?
Was it the alkene stuff?
Well, the alkene, not the alkene stuff, nope, cane. Remember the radical stuff? Right, what was the nucleophile? Right, if I'm doing a radical reaction, there's not really a nucleophile or electrophile. It's like radicals coming together, right? So which one of these looks more like a radical process? And what's the dead giveaway for a radical thing? Look at B in this, right? It has a benzene ring, which is perfectly fine. And it has Br2, which you've used for electrophilic aromatic substitution. But Br2 needed, remember, FeBr3. And in this case, instead of FeBr3, all of a sudden you see this light wave. That should be the dead giveaway. That's a radical type thing, right? And in radicals, we don't have nucleophiles and electrophiles. We have radicals, right? So yes, it does lead to this product, right? This is fine. The problem is, with these reagents, this isn't an electrophilic aromatic substitution. This is a radical process. If I exchanged out the light with the FeBr3, that's electrophilic aromatic substitution. So the key here is seeing that this is light, and that's weird. That doesn't work. Right? The thing that kind of doesn't belong. Right? The first one is Friedel-Crafts alkylation. The C is Friedel-Crafts or sulfonation, right? Adding the SO3H. And then if you look at D actually has Cl2 FeCl3. So that should be kind of a clue. Like, wait a second. To put a chlorine on, I need FeCl3. To put a bromine on, I also need FeBr3. So what's this light doing? So B is the one that's not electrophilic aromatic substitution. That's the answer. So if you see that radical, all of a sudden there is no nucleophiles and electrophiles. So really they're asking you, do you know what electrophilic aromatic substitution is? That's kind of the question they're asking here. Right. Looking at number 48. For 48, it's a mass spec question. So let's see, which compound gives this mass spectrum? So, without getting too crazy, if I show you let's show you the major peaks they have marked, essentially. They have an M peak at 120, and that means that's the highest mass. That's That's the actual molecular weight of the molecule minus 1 electron, right? Electrons don't weigh that much. Remember we talked about getting a tooth knocked out, that doesn't really change your mass that much, but it does give you a plus charge, so you see that. Then you also see a peak at 105, another peak, base peak at 77, and then way down here there's one at 43. So, if I just initially look at the mass spec here, right, mass charge, my molecule weighs 120, right? So without going ahead and adding up A through D here, because I'm not going to let you use a calculator, what you should be able to know is, right, when you get in the mass spec, what starts to happen, right? So you get your tooth knocked out first, right? You get your tooth knocked out first, and that's your molecular ion, right? That's basically what you weigh normally. But once you get that knocked out, other things start getting knocked out too. Like all of a sudden you lose a hand. All of a sudden you get an arm knocked off too, right? You start fragmenting. So these other peaks, these smaller peaks, are those fragments. But what we can tell is, right, I know a hand weighs 15. Just like you know a methyl group that gets knocked off, right? A CH3, carbon's worth 12. Hydrogen's worth 1, that's 15. So it looks like here, right, you lost, you could say this is like a minus 15, right? 15 should signal to you, wait, that's like a CH3 getting knocked off, right? Because carbon weighs 12, hydrogen weighs 1, the molecular weights. So which of these molecules in the answers could easily lose a methyl group, or even has methyl groups? So let's look at the answers. So if I draw these out quick, there's A. Here's B, C, and D. So if I show you A, B, C, and D, which of these has a methyl group that you think is easy? Which even has a methyl group that could be lost? Right. So everybody see how I got to here from 120 to 105? This is minus 15. If you see minus 15, that should scream to you methyl group, right? So which are even candidates for possible answers at this point? There should only be 2, I think. C, there's a methyl group here. I agree. And what else? A has a methyl group. These other 2 yahoos, right? This is a CCH2. That's not right. If I broke this bond right here, that's worth 14, not 15. Right? I don't know what to think of this. Right? So it's between A and C. You've now narrowed it down to 15 or 50% chance. And then from this point, you got to kind of think about which of these bonds you think is going to be easier to break and why. So one you should recognize, right, as an alpha cleavage. Right? You can break this bond, right? Because you could, if you broke this bond completely, you'd have, right, this methyl dot leave, and this bond would be left with a plus charge on the oxygen. Right? This could stabilize it with lone pair resonance. But now if you break something on a benzene ring, right, what bond is this carbon bonded to? What's the hybridization say of this carbon right here? I'm highlighting. sp2. Right? So what molecular orbitals does it have? A p and 3 sp2s. Which orbital is being used to make this bond right here? sp2. Is it good to have an empty sp2 orbital? Would these pi electrons be able to stabilize this plus charge here at all? Nope. Right? Remember that? We can't break, right? The pi electrons are like above and below the plane, and this is sticking out 90 degrees, right? Another way to think about it, right? If you have a pi bond here, I'm talking about this methyl would be sticking out at us, right? And if I made a plus charge here, right, it's 90 degrees away from that pi system. It can't be stabilized by that pi system. So it's not very likely to break this bond here. Whereas this one, if this one breaks, right, we have lone pairs right next door that can help stabilize it. So the answer for this one is A. That's the actual right answer. But, right, you recognize this methyl is gone. That's a big clue. The other piece, you could do, what's 120 minus 70? What's 120 minus 77? 120, 77, 43? Is that right? What does, if I broke off this piece, that would be what? That'd be oxygen 16, carbons 12, 8, 28, plus 15 is what? 43? There's the other way to justify it, right? It's A. Right, so by looking at, by subtraction, what is there? That makes sense, right? This is an aldehyde, that wouldn't add up. Right? Probably wouldn't add up. Make sense? So, the age-old question, what's base nucleophile, right? So, nucleophile, I like to think of as a broad term. Nucleophile is a broad term, right? It's a lover of nucleus. Right, the lover of the nucleus. So they like positively charged things. So if I love positively charged things, I myself am negatively charged. Right? Opposites attract. Nucleophiles are negatively charged. They like things that are delta plus or plus charged. Now, a base is under the umbrella of nucleophiles. Right? But bases are a particular type of nucleophile. Bases usually are electron rich or negatively charged. You can't just, it's not just negatively charged. You can say electron rich. But bases go after a particular electrophile, right? And what is that particular electrophile that bases always go after? Bases take H's. H plus, right? Bases always take hydrogens. So bases are a type of nucleophile, in my opinion. That's just a specific type of nucleophile that takes hydrogen. So if you were asked a question, right? Is this a nucleophile or a base, right? In my opinion, that's a loaded question because all bases are nucleophiles. But that's me. If you're being specific, what do you think? If they took an H, you'd probably want to say it's a base. So I think it's kind of a loaded question. But there you go. Right. Number 2 and 3 from the exam for 2015. Okay. So the first, what we have is you're shown these two things. Box number 2, H plus, and the final product is shown here. Right? So you should recognize that the nitrile has to end up on the beta carbon, right? Hopefully. So that would attack there. These electrons would go up. Right, and to balance our charge, we'd have to draw the enolate like that. So that's our intermediate. And if you look here, the H, you need to have another H end up on this carbon, on the alpha carbon. Right, and enolates, of course, are nucleophilic at the alpha carbon, not the oxygen, the alpha carbon. So these electrons would come down, take that H, and that gives us that product. Okay, so now once you have the nitro on there, the next part says the product above is reacted further with one of the products being a gas. Give the mechanism and products for this reaction. So if you remember from your Kekulé project, hopefully, maybe not, you turned a nitrile into an ester. That you did with H plus as a catalyst, and most people use excess ethanol. In this case, you're going to use excess water, and the other key here is that there's some heat. Right? So the first step is going to be having the nitrile, right? The nitrogen lone pairs, which would be the best nucleophile, right? Because nitrogen doesn't hold its lone pairs as tight as oxygen. is going to get protonated by the H+, the best electrophile. Nothing's going to happen to the ketone whatsoever. Now we have protonated nitrile. Water, which is below the arrow, so we assume that's an excess. Attacks, right? Forming not a tetrahedral intermediate, but forming an intermediate, right? Because this has 2 pi bonds. So hopefully at this point, people should be recognizing, I'm going to lose a gas, right? Well, water is not a gas, is it? Right? So I can't, right? So the only gas you should be thinking about has to involve nitrogen. And it's really going to be, it has to be NH3, right? OH minus is not a gas. Water is not a gas, right? Traditionally, right? You know, it can be obviously at certain temperatures, but, right? Presumably under normal reaction conditions, right? Even if it's heat, you wouldn't want to assume water as being a gas. Right? So we need to start getting rid of that nitrogen. That's the point. So we need to make the nitrogen a better leaving group. So we're going to do a proton transfer. And not only does this make the nitrogen more delta plus, it also makes the carbon, now it looks more like a carbonyl carbon, right? This carbon on the carbonyl more reactive. And of course there's a lot of water around, remember. So another molecule of water is going to attack. Now you have a tetrahedral intermediate. But again, what's your best leaving group at this point? Not this thing I just added. So I need to do a proton transfer. Now there's a plus charge on the nitrogen. Let me draw a little better than that. Now that's a good leaving group. So last step, we can take this OH electrons, go there. Those will go right to that nitrogen. One-way arrow, right? Because we just lost NH3 as a gas. We also regenerated H+. Remember this H right here I've circled in blue is also this H. And I've taken a nitrile and I've hydrolyzed it and turned it into a carboxylic acid. What many of you did was instead of having water attack, if you had excess alcohol or ethanol, I think it was in your guys' case, this would have been an ester. And so it's just like you did with the Keck project. Number 60 from the 1998 ACS. The question here says, which polymer could be produced by this reaction? So if we have this plus aluminum chloride, and they're saying acid, so let's say H+. So we want to know which polymer could produce this. So before we get down there and look at what's going on, let's think about the simplest way to think about this. So a polymerization is when two monomers come together, right? That's the first step, right? Polymerization is when multiple monomers, right? Poly, multiple. So let's just imagine if we just had two of these. Right, so you have two monomers. One of them is going to react with our reagents, and then once that gets done reacting with the reagents, it's going to react with this guy. Does that make sense? Right? Because there has to be an initiation for any of these polymerizations, right? So let's imagine we have two of the same monomer at first. So if I just showed you an alkene and H+, What's the alkene going to do with H plus? What's the nucleophile? What's the electrophile? Even if it's aluminum, right? If I just showed you these two things? What has a pi bond always been to you guys? It's electron rich. It always is the nucleophile, right? Because H plus is always going to be the electrophile. This has always been a nucleophile, right? Even in electrophilic aromatic substitution, it's always a nucleophile. So pretend this just attacks that. Where should I put the plus charge? Carbon 1 or carbon 2? Where's the plus charge going to be at? 1 or 2?
1.
Good. So it'll be at 1, and now there's a plus charge here. So that happened. Now I have these two guys together. So 1 and 2 and 3 and 4. Now I have a carbocation. What's my electrophile? What's my nucleophile here? What's my electrophile? The second one, the carbocation, right? What's the nucleophile going to be? The pi bond. And specifically, which new bond are we going to form, do you think?
3 to 1.
4 to 1. Because where are you going to want that plus charge to be? Right? If I said 1, 2, 4, 3, there'd be a plus charge now on. Cancel. Be a plus charge now on 3, right? Yes? And then that could keep happening, obviously. Right? So which of these looks like this? Where there'd be a CH2 in the middle, and then on either side there'd be 2 more methyls. So if you look at A, does A have a CH2 in the middle? Right? So I'm talking about carbon 4. Does A have a CH2 in the middle? No. Does B? Yes. Does C? Yes. Does D? So it's between B and D. So if you look at B, B is saying this, that, something. C is saying this, so it'll be there, and something else. Which of these looks like our thing? It's C. It's hard. Maybe it's hard to see. Maybe you'd want to do another extension here, add another piece on. But if you start to do this, you'll see that. Right? If I did another one, maybe I should just do it. If I took another monomer, and now said it was 5 and 6, which new bond are we going to form between which two? 6 and 3. And there'd be a plus charge on 5. So it'd be boom, 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 boom. It'd be 1, 2, 4, 3, 5, 6. That should start to see, right? It starts to look more like C than it, right? 1 carbon sharing 2 methyls always. That is C. So it might be a good way to approach some of these polymerization problems. Does that help?